Hello, everybody, and welcome to today's seminar. Today's speaker is Giuliamaria Menara, and she will talk to us about Eulerian magnitude homology, subgraph structure, and random graphs. Please take it away.
Thank you very much for the introduction, and thank you for the kind invitation. It's so great to be talking at this seminar. So today I'm going to talk about the work I've been doing during the past year with my advisor, Chad Giusti. And so the motivating question for this work was to figure out what kind of information about the graph G is contained in the magnitude homology groups of this graph. So now, just briefly to see the outline, then we're gonna go through all the definitions. Magnitude homology is a tool defined in the context of simple undirected graphs. And in some sense, we're going to see that a tuple of vertices is a magnitude homology generator if every triplet of consecutive vertices is contained in a small enough structure in the graph. So now we build on this observation, and we define the Eulerian magnitude homology, which is like a more strict definition of magnitude homology with a stronger connection with like these graph substructures. And then we like explore the properties of Eulerian magnitude homology, and finally we apply this definition to two random structures, Erdos-Renyi random graphs and random geometric graphs. Okay, so let's get, before we get started, we just uploaded our preprint on the archive, and this is the QR code to it. And yeah, please, I'm gonna share the QR code even at the end if you want to download it. So let's get started with the definitions. Well, we're gonna need two ingredients to define magnitude homology. We're gonna need the multiple chain and then the boundary map. So first, the magnitude chain is going to be defined as a free abelian group generated by k plus 1 tuples of vertices such that the path induced in the graph by visiting these vertices in this exact order has length L. And then we also require that consecutive vertices in the tuple are different. So let's consider this very simple graph. This is going to be our random example throughout the talk. And let's say we want to build the magnitude chain with both k and L equal to 2. Well, in this case, we either can consider tuples of three vertices such that the induced path goes back and forth on the same edge, so 0, 1, 0, 1, 2, 1, and stuff like that. Or we can like have a path that goes actually across two edges, so 0, 1, 3, 0, 1, 2, and so on. And similarly, if we want to build a magnitude chain with k equal to 1 and L equal to 2, in this case, we have well, less options because we can just pick pairs of vertices such that the minimum path, the distance between these two vertices is 2. So we just have 0, 2, 0, 3, and the converse. And well, let's just point out that the magnitude chain is going to be trivial whenever we pick a value of k bigger than L, like k equal to L is the biggest value we can pick for the k, because this is mainly because of this assumption. So let's say, for instance, we were trying to build the magnitude chain 3, 2. Well, in this case, we would need a tuple of 4 vertices such that the induced path is of length 2. But this cannot be because we're asking that consecutive vertices are different. So even if we do the simplest possible thing and just say over and over on the same edge, then we are still increasing the length by 1 every time we move on the next vertex in the tuple. So that's why this happens. Okay, so we have this first definition. Let's define the differential between two magnitude chains. And it's going to be this map delta KL. And so delta KL does this. Well, we remove one at a time the middle vertices from x1 to xk minus 1. And we keep the subtuple in the image if the length of the subtuple we obtain after removing the vertex is still a length L, and the tuple goes to 0 otherwise. So let's see how this works. We have the same demonstrative chains we completed before, and let's say we want to complete the differential delta 2 from these groups. Well, if we compute it over 0, 1, 0, then when we remove the unlimited vertex, then we're left with the tuple repeating the vertex 0, which is not acceptable by definition. So that's going to be trivial with the boundary. If we consider delta 2 of 1, 2, 3, then for a different reason, this also goes to 0, because if we remove 2, then we're left with 1, 3, and the shortest path from 1 to 3 is of length 1. So for this reason, this is going to be 0. On the other hand, if we complete differential of 0, 1, 3, then even if we do not explicitly ask for the path from 0 to 3 to go across the vertex 1, this is still going to visit 2 edges. And so 1, 3 is going to be in the image of the differential. Well, okay, we have our ingredients, matrix chain groups, differential, so we can define our chain complex, and it's possible to see that the differential is actually a boundary map. We see this showing that if we remove 2 vertices, xi and xj, in this order or in the reverse order, then the output that does not change, so everything works out well. And we can define the magnitude homology group as usual, as the kernel of the outgoing differential from a certain magnitude chain over the image of the incoming differential. So now let's compute the magnitude homology group with kn equal to 2. And so when kn are equal to 2, this is actually very nice to compute. We don't have to do any quotient because of the observation we made earlier. When k is bigger than L, the magnitude chain is trivial, so there is no incoming differential. This group is only the kernel of the outgoing differential. So we see now, if we list all the elements that are actually in the kernel of delta 2, what's happening here? We're going to find all tuples that are permutations of the vertices of the triangle, so 3, 1, 2, 1, 2, 3, and so on, plus tuples that go back and forth from one edge. So somehow the feeling is that matrix homology is accounting for the triangle, is accounting for the substructure of our graph, and it's also containing some noise. So because of this, we give this definition of Eulerian magnitude chain, where we take the Eulerian magnitude chain to be the free abelian group to be generated by k plus 1 tuples of vertices, such that we never revisit the vertex. And so somehow we call it Eulerian because we are forcing the induced path to be Eulerian. Then this is a subgroup of the standard magnitude chain. So we take the differential the same as before, the one induced by the magnitude chain, and we define homology the same as before. So now, if we take our friend graph and we do the same computation, we notice 2 things. Well, first, we're recalling that all the vertices are different, so this reduces by well, in this case not a lot because the graph is small, but in general reduces by a lot the number of elements we have to compute, which is useful computationally wise. And also the rank of this Eulerian homology group is precisely 6, which is the number of permutations of vertices in the triangle. So somehow we're detecting more precisely the fact that this structure is here in the graph. So, okay, it seems there's here some connection between the rank of Eulerian magnitude homology groups and graph substructures. And actually, we're able to prove some connection between these ranks and not really cliques, but clique-like subgraphs, like subgraphs with enough edges. So in this case, when K and L are both equal to 2, then the rank of this multi-homology group is precisely equal to 6 times the number of triangles in our graph, plus 4 times the number of chordless squares, plus twice the number of squares with one diagonal. And so when we try to generalize this, so as of now, we only have a partial result, because so when you take a bigger value of K, then the combinatorics gets very messy very quickly. So as of now, we were able to say that if we only consider the generators of the Eulerian multiple chains that go to 0 under the differential, then the number of K plus 1 complete subgraphs of G is upper bounded by this fraction. What information is given by linear combinations of generators of the Eulerian multiple chains being sent to 0 is still a work in progress. Okay. So now, I mean, these were the first results we had, and they were like kind of promising. We said, well, okay, we actually have something connected, Eulerian multiple homology to graph substructures. And we realized, okay, Eulerian multiple homology, at least on the first diagonal, we concentrate on that because, so on the first diagonal, when you look for K plus 1 tuples inducing a path of length K, then the vertices you set, they like uniquely identify the path. And so for this reason, we focus on these Eulerian homology groups, and we wanted to precisely figure out what families of graphs actually support Eulerian multiple cycles. And we do this by studying precisely what graph is induced by an Eulerian multiple cycle. So let's divide this question into steps. We start by the simple case when we have a single generator with 0 differential. So let's say we have this guy going to 0 on the differential. So what's happening here? We have this trail induced by the tuple of vertices. And what's the differential doing? It's taking out a vertex at a time. And when we take out the vertex, we want induced length to decrease. So if we remove x1, then we need this length from x0 to x2 to decrease. And this means we need this edge to be there. Now, again, if we remove x2, we need the length from x1 to x3 to decrease. And we need this edge to be there, and so on. So this kind of like graph with, in some sense, all triangles given by xi minus 1, xi, xi plus 1 have to be contained in the subgraph in order for this tuple to be a homology generator. Then the other edges may or may not be there. I mean, they don't really come into the picture of homology computation. Okay, so and this was the easy case when we have only one generator. Let's move to the less simple case. We have a linear combination of tuples with canceling differential. So let's start from this case when we have two tuples, two trails such that the differential cancel. So now let's say our first one, x bar, is trail. Now we want x bar prime to be different. So in principle, they need to be different in at least one vertex. What happens is that they need to be different in precisely one vertex. So we need something like this. We need x bar prime to be x0, x1, x2 prime, x3, x4. Why is that? Because we want the two differentials to cancel in a non-trivial way. And so what's happening here? Assuming the edge x1, x3 is not here, then when we remove vertex x2 from the first tuple, we're left with x0, x1, x3, x4. And when we remove x2 prime from the second, we're also left with x0, x1, x3, x4. And this only happens if x2 and x2 prime are the only vertices that are different between the two tuples. So this is like the new like key substructure that we need for a linear combination to cancel. Then for the same reasoning as before, we're gonna need a bunch of edges, a bunch of triangles for the differential to cancel when we remove the other vertices. And this is the graph. Then all the other edges may or may not be there. The edge that must not be there is this one. Otherwise, we just we just don't see the combination canceling, right? Because when we remove x2 and x2 prime, then the length of the path decreases, and we just don't see that. We only see the triangle. We don't see the square then. Okay, so we have like a bit of an understanding of what's going on with linear combinations. We want to like generalize this in a precise way. So what's happening when we have a linear combination of like m tuples and trails whose differential cancels? So we need a couple of definitions. We need to define what a local collection of trails is. So if we take a graph G and we take a collection of m k trails, let's call this collection X, then we call this collection local if two things happen. The first one is all trails have the same starting and ending point. And the second is for every trail xi, then there has to be at least one other trail xj, such that xi and xj agree in all vertices except for exact one. So, like more in general, we're asking for this to happen. That the trails have the same starting and ending point, and they differ in precisely one landmark. Okay. So once we have this, we need to define some like theory graph. We call it the structure graph, and we construct it in such a way that clicks and circuits appearing in the structure graph are going to encode the relations we need there to be on the coefficients on linear combination, so that the differential actually vanish. So we're going to construct this structure graph starting from a local collection of k trails. And it's going to be constructed in this way. We're going to have one vertex in the structure graph for each trail in the collection, so add vertices. And then we're going to add an edge between two vertices in the structure graph if xi and if the tuples xi and xj in the collection differ in exactly one vertex. Okay, so let's see a couple of examples. Let's construct a structure graph and see what is happening. So let's say we have this graph here on the left. Let's say this is our graph, and we need to figure out what Eulerian homology cycle, like how to construct an Eulerian homology cycle here. So let's focus for now on the first four tuples in the example. So we have 0, 1, 5, 8, 0, 2, 5, 8, 0, 3, 5, 8, and 0, 4, 5, 8. So now these are going to be four vertices in the structure graph, x1, x2, x3, and x4. And then we're going to have to add edges. And remember, we add an edge whenever the tuples differ in exactly one vertex. But now here, all these tuples, they differ in one entry. So we're going to have to add an edge here between any pair of vertices x1, x2, x3, x4. So now this produces a click in the structure graph. And the idea here is we we want the sum of all the coefficients A1, A2, A3, A4 to be 0. This is where we say the structure graph encodes relationship about the coefficients. So this is one of the structures we can have in the structure graph, the clique, and we call this the clique tree because if you, I mean, if you make the collection more complex, and then you get a bunch of cliques, and if you collapse all of them, you get a tree. This is like the reason for this name. The other thing you may the important in the structure graph is a circuit. Now, how do you build a circuit? Well, the way to build it, like theoretically, is to start with one tuple in the collection, and then change one vertex in this tuple, and then go on and on by changing only one vertex at a time, and then this is going to produce like a circuit. So for example, let's say this is our graph, and we start with the tuple x1, 0, 1, 4, 5, 8. Now, if we change only, for example, the second entry, 0, 2, 4, 5, 8, then we're able to draw this edge. And if we do something similar and do 0, 1, 4, 6, 8, then we're able to draw this edge. And we go on and on. And the idea here is that we want, when two vertices are connected by an edge, then we want the coefficient to have different signs. So you see here in the homology cycle, we're going to have +1, -1, and so on. And the nice thing here is that it's possible to show that these clique trees and circuits are actually a generating set for graphs that support Eulerian homology cycles. So if you pick a graph and a collection and a local collection of trails in the Eulerian matrix chain, then we can decompose cycles, matrix homology cycles generated by trails in X into cycles supported of clique trees and circuits, and so on the structure graph. And so, yeah, this is like a bit technical maybe, but it's like a complete characterization of what kind of families of graphs induce Eulerian homology cycles. Okay, so this was like let's say the first part of the talk. This was the first thing I wanted to talk to you about. The second thing is what's the behavior of Eulerian homology computed on random graphs. And so yeah, let's focus on Erdos-Renyi random graphs. And so the definition is an Erdos-Renyi random graph is constructed on n different vertices, and then each edge appears in the graph with a certain probability p independently from any other edge. In our work, we chose to follow the work done by Matthew Pale and Elizabeth Mackes, and so we picked p to be n to the minus alpha, and I didn't specify here. I'm sorry. Alpha ranges from 0 to infinity. And so the first question, the first thing we want to figure out is, when do we actually have homology? So we want to find a vanishing threshold for Eulerian homology on the first diagonal when K and L have the same value. How do we do this? Well, we figured out before what kind of graph induces a homology cycle. So we're going to count the occurrences of those specific graphs in our Erdos-Renyi graph. So as before, let's start from the simpler case. Let's say we have a single generator that is a homology generator, and so the induced graph is going to be the one we completed before, the one with all these triangles. So now this graph is going to have different vertices, so we can choose them in n2 k plus 1 ways, and then it's always going to have these k black edges that are the edges included in the original trail, in the original path, and then these k minus 1 blue edges that need to be there so that the differential vanish. So this gives a total of 2k minus 1 edges that all appear with this probability because they are independent. And then we need to account for some number of permutations of this graph. And well, going on with the computation, what we obtain is that the number of these graphs vanish in our Erdos-Renyi random graph when alpha, the exponent alpha, is bigger than this fraction. So, okay, this is like the first part of the vanishing threshold, the one for the easy homology generators. Let's move to the more complicated one, to the ones given by linear combinations. So now, how do we construct those graphs? Well, let's start from the graph we saw just now, and let's say we want to build the graph induced by the Eulerian homology cycle 0, 1, 2, 3, 4, 5 minus 0, 1 prime, 2, 3, 4, 5, and so on. So the first thing we need to do is make this 1 prime and 2 prime appear and actually matter. So what we do is we need to remove these two edges, 0, 2, and 1, 3, and build squares with the 1 prime and 2 prime. So we're going to have these structures here appear. Then here we want to have the trail 0, 1 prime, 2 prime, 3, 4, 5. So we're going to have to add this edge 1 prime, 2 prime. And then, well, we need this other edge 2 prime 4 just for because we need the triangle to be there. We need the differential to cancel when we remove the 3. So now, what's happening here? Like, the thing is, if we start from the easy graph, from the one induced by a single generator, the way to build the graph induced by a linear combination was removing m edges at the beginning to produce the squares. So we're going to have a term 1 minus p to the m, accounting for the edges that must not be there. In our case, 0, 2, and 1, 3. Then for every edge we remove, we build a square there, and so we add 1 vertex. So the number of vertices here is going to be k plus 1 plus m, and then all the mutations. And then how many edges do we surely have in our graph? Well, it's going to be the 2k minus 1 we had before, minus the m we subtracted to be the squares, plus the 2m we added here, because for every edge we cancel, we need to add 2 for the squares. And maybe, potentially, we have to add more. For example, here we also added 1 prime, 2 prime, and the 2, 4. So this term might, this exponent might be bigger, so this might actually be this number might actually be smaller. And what it turns out is that the vanishing threshold for the number of these graphs is smaller than the one for the simpler structure. So globally, we're able to say that if we have an Erdos-Renyi random graph where we take the probability p equal to n to the minus alpha, then the Eulerian homology groups on the first diagonal vanish if the exponent alpha is bigger than this fraction. And so, well, to go towards the conclusion, after this result, the natural question was, okay, so now we know a threshold, we know when we do not have a Eulerian homology, and when we do have homology, how does it grow? How does it go to infinity? And so here we again follow the work done by Matthew Carroll and Elizabeth Mattis, and we were able to obtain these two results. The first one telling an expectation of Martin homology Betty numbers on the first diagonal, and the second one providing a central limit result. And we had this hypothesis here on the probability, which is actually, this is actually saying that we have enough edges in the graph. When n is going to infinity, t is going to 1. So this is telling us that the graph is dense enough. So we have enough edges to build our subgraphs that are going to create Eulerian homology cycles. And okay, the last part of our work is to reproduce this analysis in the context of geometric random graphs on torus. And I'm not like really getting into that right now, but just broadly, we were able to get similar results, but we had to use like quite different counting techniques. And the main problem was that when you have geometric random graphs, we're actually like building the random graph in a metric space. And so you have triangular inequality. And because of triangular inequality, the edges are not independent. So, I mean, this complicated things a bit, but nevertheless, we could obtain similar results both for the vanishing threshold and for expectation of the Betti numbers. And so yeah, to finish, our contributions in the paper were first one to highlight the existing relationship between Martin homology groups and the subgraph counting problem, and then building on this observation, define Eulerian Martin homology to like emphasize this relationship. Then we provided a characterization for subgraph induced by Eulerian homology cycles. And finally, we analyzed the behavior of Betti numbers of the first diagonal, both for the Erdos-Renyi model and the random geometric graphs. And these are the main references we used in our work. And thank you very much for listening.
Right, thank you very much. So before we move to questions, I would like you all to I would like to ask you all to unmute yourselves and clap for the speaker. Right, thank you very much. So now to questions. Okay.
I can ask sort of a strange question to start. It might not make sense, but can you define magnitude homology for infinite graphs and maybe special infinite graphs that are sort of a limit of finite graphs? I'm thinking, like you build a Rips complex of finitely many points on the circle, or you have a scale R and you connect 2 points if their distances within R, and you sort of have a finite number of points on the circle. But if you sample more and more points, maybe there's a underlying infinite thing that you're converting to, like all vertices on the circle.
So the truth is, I didn't think about infinite graphs. My guess is I don't know. I should think about this. I'm thinking what might break.
Uh-huh.
But
Just getting started, it might all break. I don't know.
um, yeah, well, I don't know. Maybe I actually never thought about that. Yeah, I'm sorry.
No, no problem.
Okay, I'll ask a question. So at the beginning, you define essentially all of your notions for two values, K and L. But then afterwards, like at least let's say in the last part of the talk, you very often consider K to be equal to L, right? And you said something about, I forgot which one. If one is bigger than the other, then you always get trivial homology, but not necessarily the other way around. So my question is, um, like, does the fact that you consider K equal to L have some, do you have a reason for it, or did you also prove things for K different from L, and how much more difficult is it, or is it more difficult?
No, so the reason why we consider only K equal to L is that there is like a more precise interpretation for what's happening. Like, let's go back. Well, yeah, let's see. When K is equal to L, then like the vertices you pick completely determine the path you're going through. So if I gave you 1, 2, 3, then you're going through these two edges, and I know precisely what I'm doing. And so this was the first reason. And also when K is equal to L, we have like that interpretation for counting click like subgraphs. So we have like a motivation for for which kind of subgraphs we were counting. When you pick K smaller than L, then the complexity grows very, very fast, because when you I need a bigger graph. Like here, okay. If I just give you like let's say the graph is much bigger around here. If I just give you 0, 8 and nothing in between, then you might go through 0, 1, 5, 8. You might just go through 0 to 8. I mean, there's so many things that might happen, and the combinatorics gets very messy very quickly. So I mean, it's actually like a work in progress. We're thinking about what's happening in like lower diagonals when K is smaller than L. But yeah, right now I don't have a precise interpretation or like characterization of what's happening.
But if I never know which one is K and which one is L, but let's say
I'm
that
sorry.
one of them is almost 0. So like if you consider like only really long paths, right? Because right now you consider paths of length 1. I mean, sure, for two vertices you might have so many possibilities to get from one to the other, but on the other hand, there are only as many like tuples that you can
Sure,
consider.
but the differential gets complicated, because the only thing you know about the differential is that when you remove a middle vertex, then it goes to 0 if after the removing of that vertex, the path decreases. So if like here between, like if I do 0, 1, 5, then if I remove 1, the length between 0 and 5 has to decrease from 2, and it can only be 1. But if the length between 0 and 5 is 6, I have already 5 possibilities. So it's like a wide range of possibilities. Yeah.
Well, it sounds like a exciting new area to dive into.
I guess if somehow you account for all the possibilities, like if you grade if you say like the induced length has to be smaller than 5, so you pick all the 4, 3, 2, 1, and you account for all the possibilities, then somehow you're still counting clicks, and maybe in a more precise way, because you're counting all the substructures contained between those two vertices. But yeah, that's just an idea.
I wanted to ask if you could comment on how hard this homology is to compute. I mean, maybe when k is equal to L, or maybe when they're different. And in particular, did you use any computations to sort of guide the results you prove about Erdos-Renyi?
I mean, so the computational complexity is highly dependent on the density of the graph. So for example, for a complete graph, it's exponential. So I did use like some code but it's a very naive code. Like I literally wrote the definition. So the computations I did were for like small graphs, like manageable graphs. And I mean, I think it would be nice to actually work on an algorithm to compute this thing more quickly, because I mean, this relation with like dense substructures contained in the graph, I think it's interesting. And so, I mean, if we were able to like somehow split the graph in tiny pieces, then even if the tiny piece is dense, it's not so difficult to compute the Eulerian homology. So yeah, maybe something like that might be interesting. But yeah, I mean, in general, it's the complexity is very high.
Thanks.
Any more questions?
Yeah, I will have a question.
Hi,
Hi, Julia. I got very excited when you mentioned that you have now some results on the random geometric graphs. So I was wondering whether there are some implications on the magnitude function of this point cloud, or what is in general the relation between your Eulerian magnitude homology and the magnitude function. And I mean, the goal in the end would be like, I was wondering if you can have some kind of central limit theorems like you have for the Betti numbers. One can get some central limit theorems for the magnitude function, maybe some functional central limit theorems. I think that would be really cool, but I don't know whether this is related and how.
Well, so the thing is, I didn't really think about the magnitude function. Like, what I can tell you is, if you decategorify Eulerian magnitude homology, then the Eulerian magnitude you get is going to be a polynomial instead of a power series with standard magnitude. So this might actually be helpful, because then, I mean, if you figure out what the coefficients of that polynomial are telling you, then I mean, there's a lot of computational algebra you can do on that, and but yeah, I don't know about the relation with the magnitude function.
Okay. Cool. Thanks.
Are there any more questions? Okay, I have one more question. Coming back almost to the beginning, you had this expression with like 6 times a triangle plus 4 times a square plus 2 times two triangles together. Exactly. I'm not much of a graph theorist, and to me this looks a bit like I mean, okay, it has 2 pluses, but some kind of an Euler characteristic. Like, is there any relation? I don't know, like Euler characteristic of what should it be, but
well, I mean, I don't know either. It is a work in progress. Like the thing is, well, it's more or less what I was telling Nicholas before. If you compute the Euler characteristic of the Eulerian magnitude chain, then well, you are going to get a polynomial, and what I think is the coefficients of this polynomial are going to count, like, I don't know, the first coefficient, the number of triangles, the second coefficient, the sum of these two, like square plus cosine square. The third coefficient is going to count something else. So you're gonna have, like, in the Euler characteristic of this thing, the coefficients are going to account for different kind of subgraphs. So something like this sum. But yeah, I don't have a precise statement yet.
thank you very much.
Mhm.
Are there any more questions? If not, thank you again, Julia, and I'll stop the recording.
Thank you very much for listening, for inviting me.